We're about to work through some practice problems. Now, for the best effect, you should always try these problems by yourself first. If you're watching this video for the first time, you can use that pause button when you see a problem and try it yourself. Unpause to see if we agree. An alternative is you can follow the links below and you can find a copy of these problems which you can work out at your leisure. All right, let's get going. So here we have a lovely problem. For one thing, there's no words, because you know how much students don't like word problems, but sometimes words can be a little bit helpful to tell us what it is we're exactly trying to figure out. But let's see if we can't just sort of say, we see what's going on. What do we have? We have two integrals, and we're adding together, and we're told that they're equal to one of these. But if you look a little closer, we say, hey, you know, in our original integrals, we have the order dy dx, but in these integrals here, they all have order dx dy. So we're changing the order of integration. So this is about changing order of integration. It's a very common problem. So we say, okay, so now we know what we're trying to do. We need to figure out how to do it. So what we're going to do is we're going to start with our description. And there is a description of our regions. It's embedded into our current integrals. So remember that these link. So we have that, for example, here, the inner layer links with the inner bounds, and the outer layer links with the outer bounds. So we would read this as x goes from -3 up to +1. Where y goes from 4 minus root x plus 3 up to 4 plus root x plus 3. All right, great. Now that's the first one. The second one, we're going to do the same thing, right? We're going to connect the inner layer, inner bounds, outer layer, outer bounds. So we're told that from the outer layer, x goes from 1 up to 6, and that y goes from -4 root x plus 3 up to 6 over x. All right, so this is our current description. Now, let's see if we can't turn this into a picture. All right, well, let's start with these functions here. Now, as we're looking, what do we see? Well, they're a little bit unusual here, but if you just sort of try to say, at its core, what function are we seeing? It looks a lot like a square root, isn't it? Yeah, if we ignore the 3 and the 4, those are constants, that's a square root function. Like, oh! So this is like a square root where we've done things to it. So what things have we done? Well, if we just start with a normal square root and we were to add or subtract on the inside, that's a horizontal shift left-right. Now, +3, that's really -3, means we've shifted. So instead of starting at 0, we're starting at -3. And that makes sense because we're having x starts at -3. The minus will turn it upside down. And this 4 will have a vertical shift up. So it's like we're moving it up. So in particular, we say, okay, so if we were at this point, so we're at -3 for x, and we're at 4 for y, then what we have is a square root, one square root opening up, that's the +1, one square root opening down, that's the -1. Well, let's go and see where they're at time 1. Okay, so at time 1, what do we see? Well, let's plug in 1. So 4 minus square root of 4. That's 4 minus 2, which is 2. Okay, so that says we're there. So we're at the point x equals 1, y equals 2. All right, so we have our square root doing something like that. Now, positive 4 plus square root of 4, that would be 6. That means we're up here. And so Again, we're moving up and a square root like that. So it looks like, two square roots together look an awful lot like a parabola. All right, well, we'll get there. We'll get there. Don't worry. Don't worry. Okay, so that's our first region. And just to emphasize, this is how we're integrating top to bottom. All right, there we go. Now, in our second region, we're going to start at 1. And what do we have? Well, the bottom curve is actually just a continuation. And so where are we going to stop? Well, at 6. Where are we going to be? Well, plug in 6. 4 minus 6 plus 3. Square root of 6 plus 3, that's 4 minus square root of 9. 4 minus 3 is 1. And so by the time we hit over to 6, so let's say it's over here. And by the way, your pictures don't have to be super accurate. We're going to get down there. All right, so that's that curve. Okay, and now the top curve is 6 over x. Now, at x equals 1, if you plug in 6 over 1, you're at 6. Oh, that's very nice. And if you plug in x equals 6, 6 over 6, you're at 1. Ooh, that's also very nice. And so it's the 1 over x curve. It's doing something like that. So we're going to be going some down, something like this. All right, so there's our curve here. All right, good, good. All right, and that's how we're currently integrating. Now, that's our current setup. Let's talk about where we're going. So I'm going to mark these curves. Y equals 6 over x. And then we have, of course, y equals 4 plus square root x plus 3. And down here, we have y equals 4 minus square root x plus 3. All right. Well, the nice thing is we know where we're going. We're going to go and switch. So instead of slicing up and down, we're going to be slicing left and right. And so we say, okay, well, what's happening? Well, as we slice left and right, we see that we're going between these curves. And so consistently, there seems to be this curve on the left and this curve on the right. So we need to figure out what those curves are. And in particular, we want to solve them for x as functions of y. Well, if y equals 6 over x, that one's pretty easy. We just multiply by x, divide by y. X equals 6 over y. Now, what about these two curves? Well, let's just say y equals 4 plus or minus square root of x plus 3. We can subtract 4. Y minus 4 equals plus or minus square root of x plus 3. Square both sides. And y minus 4 quantity squared is equal to x plus 3. The nice thing is the plus or minus goes away. Y squared minus 8y plus 16 equals x plus 3. Or finally, subtract 3. X is y squared minus 8y plus 13. Just as you thought, right? Oh, maybe not just as you thought, but that's okay. And the nice thing is, it's always that, right? See, there's no two cases. It's just one curve, one function that covers it all. All right, so what's the setup going to be? Well, for the outer layer, we say we're going to go from low value to high value. Low value of y, high value of y, 1 to 6. So we say, okay, we need 1 to 6. That says A, B, and C are in contention. D and E, nope, they're not going to work. They have the wrong bounds for the y value. Now, what about the inner layer? Well, we're going to go from low to high. So from low to high, left to right. So the low on the left, that's your y squared minus 8y plus 13, to the high on the right is 6 over y. So this should be our lower bound, And this should be our upper bound, and that means our answer is B. And there we go. All right, woohoo! Nice! Now, I will comment, I'm probably going to go really slow here, and so don't be like, oh my gosh, how are we expected to finish all this in time? I'm taking my time because I want to explain things and try to help you see the picture. On a real test, I would do this a lot faster, as would you. And so don't panic. You'll have plenty of time. With practice, speed will come. All right. Well, we have a problem down. Let's keep going. Which of the following is a sketch of the region for the integral 0 to 1, 0 to x squared, 0 to 1 minus z, f of x, y, z, dy, dz, dx? Whew, okay. Wow, interesting. And we have a bunch of shapes. None of them look like any of the others. So the good news is, even if we weren't entirely sure where x, y, and z are, we're going to have to figure it out in the end. And so no ambiguity in the end. All right, well, what should we do? Well, we can do what we always do. Say, let's first off think about what the bounds are telling us. Now, the outer layer, that tells us that 0 is less than or equal to x, less than or equal to 1. The inner layer, or I should say the middle layer, 0 less than or equal to z, less than or equal to x squared. And finally, the innermost layer, we have that 0 is less than or equal to y, less than or equal to 1 minus z. Now, remember how it goes. The outside is between two numbers, the middle between two curves, and here between two surfaces. Now, if we're thinking about trying to narrow things down, we can really focus mostly on these parts right here. Usually this will be very hard, especially since it didn't give us any numbers here. Well, let's talk about this layer first, the outermost layer. So y equals 0, what does that correspond to? That corresponds to the xz plane. Now, if we think about our normal labeling, so we would label our sides x, y, z. Go ahead and mark that here for reference. And, well, what's going on here? Where is the xz plane? Well, the xz plane would be over here. So we're going from this sort of flat side, and you'll see in each one of these pictures, we all go from the xz plane, so that's good. Now, what about y equals 1 minus z? So that's a little bit different. So again, I'll just sketch for y equals 0, just so we remember that corresponds to the xz plane, and that's this part right here. All right, xz plane. Now, for y equals 1 minus z, that feels like, whoa, hold on. I thought this was 3 dimensions. Where's your x? There is no x. So wait, how does that become a picture? Well, what's going to happen is that we're going to have, think of it in the first off, just yz plane. So this is your yz plane back here. And y equals 1 minus z would look like a line segment, and then you just copy it. In other words, drag it left and right in the x direction. So you're a plane. So we're going to this sort of tilted plane here. So, okay, so that's the plane we're going to. So we should have, if we were moving left and right in the y direction, we should be going from the xz plane to this flat plane. And if you look, each one of these actually does exactly that. Okay, so good, but not for us. That doesn't narrow anything down. Okay, so nothing gets narrowed down by this condition here. But that's okay. We have another condition, which is, let's look at these pieces here. In other words, now just sort of the two outermost layer. How do we get intuition? Well, for this, look down the y-axis. And what we're going to do is say, what do we see? So when we look down the y-axis, well, we're going to see the xz z plane. So in other words, we're looking straight down. So it's like the y-axis is right there. We're told that x goes 0 to 1, and z goes 0 up to x squared. So we have this z equals x squared curve. And so when we look down the y-axis, we should see this shape. Okay, now what does that tell us? Well, that tells us that if we were putting this in our diagram, like we see here, that we should see what you could call it a projection or a shadow. But in terms of just translation here, so this is your x, y, z, we should be seeing this shape. So which axis, when we look down it, do we see this shape? And we can sort of spot these shapes, right? Let's just color them in, right? We've got colors, and we say, okay, well, it's not C. That's definitely the wrong shape. Not B. B is over here. That's not going to work. Not A. Again, A is up here. And it's not D, right? Because D is coming down. But look at this one. It's a match. All right. So what does that tell us? Well, it tells us that the only one which is matching must be the right answer. So the answer is E. All right, good. Good. So this is going to be a nice thing to be able to do. Can you visualize in 3D? Can you go from a 3D image? Can you get the bounds? If you have the bounds, can you pick out the 3D image? That's an important skill to have. And this comes back to the idea of this class, even this particular test boils down to, can you think geometrically? So it's good to start practicing and thinking, okay, what do your surfaces look like? Where are you integrating when you look down the axis? What's going on? And if you can help build that up, that intuition, you're going to be great. You'll be fine. No need to worry. It's all going to be okay. Let's find a curl. So here we have a curl. Now, let's remind ourselves what a curl is. A curl is essentially like we're taking a derivative, but in particular, it's a very special case. We're going to start with a 3D vector valued function, and we're going to end with a 3D vector valued function, which means our input better be a 3D vector valued function, and our output better be a 3D vector valued function. And good news, that doesn't narrow anything down. Wait, that's bad news for us. Well, let's just call it news. Okay, but how does it work? So the curl, this involves your del operator. So the curl of a vector valued function f is del cross f. Now the way I remember to do it, and I would encourage you to think of it this way too, it's a cross product, so you have your ijk. Your del is your partial derivatives. Partial x, partial y, partial z, and then you put in your entries of f, m, and p. And now take your determinant and simplify, and hopefully, as long as you're careful, and of course we're going to be careful because it's an exam, right? It's a great time to be careful. We'll get the right answer. Okay, well, let's begin. Here we go. We'll take I, j, k, partial x, partial y, partial z, and m, n, p. Okay. Well, I should have written down what m, n, and p are. Okay, all right, let's write that again, Steve. No problem. Partial x, partial y, partial z. Now let's pay attention. M, y squared. N, x squared plus z squared. P, y cubed minus 3x. Good. All right, remember determinants. You've got your down diagonals, and then you have your up diagonals you have to subtract. So I, partial y, y cubed minus 3x. Well, that's 3y squared in the I direction. All right, now, by the way, we can stop. Which one of these has a 3y squared in the y direction? Just A. But we're going to go ahead and finish it. See, that's one of the nice things about multiple choice is you don't have to answer it. You just have to know enough to know which one's correct. And so this was, hey, 3y squared better be in the first entry. A is the only one that has a 3y squared in the first entry. We're good to go. But let's go ahead and keep going. J, partial z, y squared. Well, there's no z, so that's 0j. K, partial x of x squared plus z squared would make 2x, and that's in our k direction. All right. Now, those are your down diagonals. Don't forget your up diagonals. And when you do your up diagonals, you also have to remember you're subtracting. Okay, so here, y squared partial y, that's going to be minus 2y, right? Because we're going up. So minus 2y, k direction. Here we have x squared plus z squared, partial z in the I direction. Okay, partial z of x squared plus z squared is 2z, I direction. We're going up, so minus 2z, I. And our last one, y squared minus 3x, taking partial x of that, that'll be minus 3. That's in the j direction. So subtract minus 3j. And put it all together, we get in the I, 3y squared minus 2z, j, 0 minus 3, k, 2x minus 2y. And there we go. And indeed, it really was that whole thing. But like I said, oftentimes, if you just know, say, one entry, sometimes even just a part of one entry, that's enough to get your whole answer. So take advantage of the fact that you have multiple choice. Why not? We should enjoy it, right? Of course, of course. Which of the following vector-valued functions is conservative? Ooh, conservative. Okay, now how are we going to figure that out? And what does being conservative mean? Well, conservative is another way of saying that it comes from a gradient. So it's a gradient of some function. Now, one way we could answer this is just say, let's find potential functions. And the one where we can find a potential function, that's got to be our answer. However, there's going to be some obstacles here. Notice in this one, there's a sine of x cubed. In this one, cosine y to the fourth e to the y squared. Here you have an arctangent y to the fifth. Here you have a z squared plus 1 to the z. And let's see, and here, yeah, everything looks pretty straightforward, but I will point out this one looks, oh no, that one's going to be terrible. Each one of these has a piece which is just like, we're not going to be able to find those antiderivatives. But here's sort of the fun thing. When you're trying to figure out what's conservative, there's parts that you can ignore and parts you have to pay attention to. So let's talk about understanding what can you ignore, what do you need to pay attention to. So what's going on? Well, when we have a conservative function, what do we look like? Well, we look like f sub x, f sub y, f sub z. And so in particular, we say, okay, so the first slot takes derivative with respect to x, second slot derivative with respect to y, and third slot derivative with respect to z. Now, notice here, this only involves x, and it's in the derivative with respect to x slot. So the only place it really can show up when we try to take an antiderivative is when we do this f sub x integral. What I'm trying to get at is, if you're in the x slot and you only involve x, you're not going to determine whether or not you're conservative. It doesn't matter. If you're in the y slot and you only involve y, that won't matter. You can be as terrible looking as you like. It will not change whether or not you're conservative. And finally, if you're in the z slot and only involve z, same thing. That will have no effect on whether or not you're conservative. So what does matter? What matters is the interaction. So in other words, things that show up in multiple places, there needs to be consistency. All right, so here's what we're looking for. We're looking for pieces which should occur in multiple slots. We need to make sure they're consistent. All right, so let's look at this part. Part A, 2x e to the z. Now notice, what would this tell you? Well, it says if you integrate with respect to x, we should have an x squared e to the z. Well, let's compare. Since that has a z, we say, hey, there's an x squared e to the z, but there's a minus. When you integrate with respect to minus, you say, well, you get a minus x squared e to z, right? Well, because in this case, we're integrating with respect to z. This is an inconsistency, not compatible. So it can't be A. All right. Well, what else can we do? Let's look at another one. So here's something, zy squared. Now that involves things that aren't x. It's in the x slot. So it says, okay, you should have an x, y, z squared. Now here, what does this say we should have? Well, if you integrate with respect to y, you should have an x, y cubed z. Order's all over the place here. But then here, if you integrate with respect to our z, this is an x, z, y squared. Whoops. Yes, okay, all right. I put the square on the wrong thing. It should be there. So xy squared z versus xy cubed divided by 3. That's, you can't really see that divided by 3 very well. Z versus our xzy squared. Now what's the problem? These aren't the same. Not conservative. Oh my gosh. Not looking good for us. Okay. Well, it's all right. We still have options. 2xz. Okay. Well, that involves both x and z. So this would say you should have an x squared z. Well, look in the z slot. Integrate with that with respect to z. You do have an x squared z. So that's good. Okay, so that checks out. Well, here we have a sine of y. All right, well, that's in the x slot. So if you integrate with respect to x, that's x sine of y. And here, come here, if you integrate this with respect to y, that's x sine of y. And you say, okay, well, that's checking out as well. And we already said, hey, don't need to worry about that arctangent y to the fifth. Oh, everything's good. So C is our answer. C is conservative. Now, I want to keep going and talk about reasons why the others aren't, and also another way you could have done this. All right, well, let's look at D. What do we see here? Well, we see a 3x squared z. That would say, all right, we need to have an x cubed z. So we look over here in z, and what do we get? Well, we get an x cubed z. Okay, that's fine. So parts of it work out. What about here? Cosine y. Integrate with respect to x. That's going to be x cosine y. Now here, look in the y. X sine y, oh, that looks promising. Integrate that with respect to y. What do you get? Negative x cosine y. Doesn't match. So it's not going to work. Right? It has to be exactly the same. So they're not compatible. All right. Well, one more, right? Sure. E. What would we have? Well, let's start with this piece right here. 3x plus 2y quantity squared. If we integrated that with respect to x, what would we get? Well, basically this 2y is just a shift, and so that would be an x plus 2y quantity cubed. Now, what about here? Well, if you integrate, coming to the y term, x plus 2y squared, you integrate that, well, you're going to add 1, divide, but you're also going to divide by 2, and so what do you end up with? Well, you end up with 2/3 x plus 2y cubed. They're not the same. They don't match, so it can't be E. All right, And there we go. Now, as we've been talking here, you're probably starting to think, wait, what? I lost the story. What are you doing, Steve? Well, essentially what I'm doing is I'm more or less just comparing pieces. And so I don't want to go through and do all the formal work, but I'm integrating the first slot with respect to x. I'm comparing it with the third slot with respect to z. I'm just saying, well, am I consistent? It's a consistency check that we're implementing here. Now, what are some things that you could do? Well, the nice thing is if you have a function that's three-dimensional, if you want to test if it's conservative, you can do the following. So you're conservative if and only if, and I have to remember how to spell conservative, and dramatic pause. Whoa, what could he be saying? You're conservative if and only if the curl of your function equals 0. So you could take the curls here, but the problem is that sounds like work. And we'd like to try to avoid work if we can. So finding the potential, that sounds like work. Doing the curls, that sounds like work. So try to find a happy medium. And in essence, I'm trying to do a happy medium, which is just to say, check for consistency. You're going to be conservative if you have consistency. And in other words, you're able to reassemble the pieces and get the function, your potential function. So there's lots of ways to do it. Do what works for you, all right? Because on multiple choice, there's no partial credit. We're not going to judge your techniques. Do what works for you. Whatever it takes, as long as you get the right answer, you're great. All right. Good. Let C be the curve parameterized by t cubed root 3t squared 2t. And we have time goes from 0 to 1. Okay. Then we're going to do an integral along the curve of 2z minus 3x ds. In other words, a line integral. Ha ha ha! Okay, good. Now, many line integrals are messy because you have the ds part. And the ds part is really where you're going to put a lot of effort into it. So let's remind ourselves how this works. So the moral of the story is we want to try to push line integrals back into the kind of integrals we're used to. Integral from a to b. So instead of like some winding curve, just like zoop, a to b. So that's what we're trying to do. And we can pull it off. So how do we do it? Well, what we're going to do is rewrite the integral in terms of the parameterization. So everything is going to be replaced in terms of our parameterization. So for instance, here we have our x, our y, and our z parts. So the 2z, well, that's going to become 2 times 2t. The 3x become 3 times t cubed. Okay, so that's that part. That's easy enough. The ds, which is the part which I'm dragging my heels on, that can be the part which will make or break us. Well, the question is it nice? So let's do it down here. So ds is equal to the square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt. All right, so in our case, this becomes, well, the derivative of t cubed, 3t squared. Square that. Derivative of y prime, 2 square root of 3 times t, square that. Derivative of z, 2. Square that. All right. Now, this will be 9t to the fourth. 2 squared is 4. Square root of 3 squared is 3. 4 times 3 makes 12. T squared. And plus 4. All right. Now, if we've lived a really good, clean life, and our instructors love us, and I really firmly believe that they at least like us, not just tolerate us, they at least like us, and I do think that there's some love going on here. There should be something nice. Now, that something nice could be maybe there's some kind of substitution that you can make on the inside that will match with what's here. But the other nice thing is, what do you hope for? The hope is that what's inside simplifies. And in particular, in a perfect world, what should be true? It should be a square. Okay, well, are we there? Is it a square? Now, you might say, it's a quartic, fourth degree polynomial. How do we do that? Well, think of it as like t squared squared. And like, that doesn't sound so bad. So if it were a perfect square, it'd be 3t squared, because that's, square 3t squared, you get 9t to the fourth. And here's the small term, that would be a 2. And then you say, well, that's a plus in the middle. Now, does that work? Let's check. So it'd be a squared, good. B squared, good. 2ab. So 2 times 3t squared times 2 is 12t squared. Wow, almost like it was meant to happen, because it was meant to happen. So we end up with no square root, just 3 squared plus 2 dt. All right, so that's your ds. All right, so 3t squared plus 2 dt. So we update the function in terms of t using the parameterization. Using the parameterization, we find ds in terms of t. And then our bounds, the integral along c, now becomes an integral in terms of t. Integral 0 to 1. And now we have our problem. Okay, so this is not so bad. And it is a problem which involves integration, but the whole test involves integration. We got to expect to do some integral at some point. All right, so let's first off, we'll FOIL. So let's see, this is equal to the integral from 0 to 1. So we have 4t times 3t squared, and that would make 12t cubed. Then we'll have 4t times 2, that makes an 8t. Then we have minus 3t cubed times 3t squared, that makes minus 9t to the fifth. And then minus 3t cubed times 2 makes minus 6t cubed. Well, we can put those two together. And so this becomes integral 0 to 1 of minus 9t to the fifth, and then 12 minus 6 plus 6t cubed plus 8t dt. All right, good. We're getting close. We're almost there. So let's integrate. And, all right, add 1, divide by the new power. So minus 9 over 6, t to the 6. Add 1, divide by the new power. 6 over 4, t to the 4. Add 1, divided by your new power. 8 over 2t squared. Evaluate from 0 to 1. Now when you plug in 0, everything's 0. 0. Friend, we like 0. Okay, so plug in 1. Nice thing is 1 to any power is 1. So we're really close. So we just have our coefficients. Well, let's see what we have here. Minus 9 over 6, also known as minus 3 over 2. 6 over 4, also known as plus 3 over 2. 8 over 2, also known as 4. Well, these two terms cancel, so we're left with 4. All right, so there's our answer. 4. Nice. Nice. What a beautiful problem, right? See, line integrals can look scary because of the ds part, but in certain cases, in other words, ds is nice, it's not so bad. So know the procedure. And I will say there's two things that can happen in line integrals. So one is this type of line integral where you actually have to go through and do the ds. There's another type of line integral conservative line integral, which uses a completely different method. So make sure you know and are able to recognize both situations. And practice both, because who knows what's on the test. Well, someday soon we'll all know, right? Okay, good. Set up an integral in polar coordinates that finds the volume under the surface z equals 10 plus xy over the region R, which is the set xy, which is x minus 2 squared plus y squared less than or equal to 4. All right, well, let's think about this. Now, what's being tested here? Well, basically, we're just testing on our ability to do polar coordinates. Okay, so let's think about what we have here. Now, we're asked to find volume. So we can start by saying, well, we know the way we find volume is we're going to integrate over our region our height. So if you take height times area, that's a piece of the volume. That's the volume over that little piece. You add up all those little pieces of volume, there's your total volume. All right, cool. So that means that we're integrating over our region 10 plus xy, because our height is the surface, because we're going from the surface over the region. So from 10 plus xy down to 0. And dA. All right, great. Cool. And now we need to start thinking about how we figure this out. Now there's a couple of things to know, and we'll make some notes here. We do know, for instance, that in polar, we have that x is r cosine theta, y is r sine theta, and x squared plus y squared equals r squared. And basically, that's our go-to collection of facts. Now, we have some space left, so there's one other thing we'll write down, which is that when we're going to polar coordinates, we remember that every integral always has 3 pieces. We're going to tell this again. It's a good story. There's the function, which people put a lot of thought into. There's the bounds, which people put some thought into. But then there's the other part, and the other part is how you're breaking things up, and that depends on your coordinate system, and you have to make sure to account for that. So for us, when we're switching into polar, we get that dA is r dr d theta. So there needs to be an r there. So if there's not an r, that basically says, whoops, you missed something. And that's a common place for people to get tripped up. So make sure you remember that and you're looking for that. Okay, so let's see what we currently have. With doing nothing else than just updating the function and our dA. What do we have? Well, this is going to be the integral over the region, and we have 10 plus r cosine theta, r sine theta, r dr d theta. All right, so let's see how many options are left. Well, we have r squared. Now notice none of these have an r dr d theta, but that's okay. You could move it in. They didn't have to write it in a nice way. So this could also be written as 10r plus r cubed cosine theta sine theta. So maybe that's what we're looking for. Okay, so B works, but A doesn't work. It's short in R. So A is out. B is still in. C, same thing. It's short in R. So that's out. D is still in. And E, again, that's out. Okay, good. So now, just knowing the inside, it's a coin toss. 50-50. Okay, well, how do we figure that out? We're going to have to deal with our region, because that's the part we haven't figured out yet. Okay, so let's talk about our region. Well, it's a circle. Now, it's not centered at the origin. It's been moved over. So where are we now centered? At x equals 2, y equals 0. So in terms of the xy plane, our circle is here. All right, so here's our region. And we say, all right, pretty. It's very nice. Now, what are we going to do? Well, we want to convert that description into polar. And so let's focus on our equation. X minus 2 squared, that's x squared minus 2x plus 4 plus y squared equals 4. So I'm just on the edge of the circle. The 4's cancel, and x squared plus y squared, those just naturally go together. Whenever you see x squared plus y squared, that's a, hey, have you thought about polar? Polar seems like a really good idea. You should think about polar. You know, that's a signal that, hey, you're right, I should think about polar. All right, now we have our list here. So x squared plus y squared, well, that becomes r squared. 2x, well, that becomes, whoops, I wrote 2. I shouldn't have been writing 2. I didn't square that right. Because x minus 2 squared will be x squared minus 4x. Oh my goodness. I am sorry about that. You know, be careful. No matter how many times you've done problems, small mistakes will catch you. It's, you know, it's a squared minus 2ab. I forgot that 2. And then plus b squared. Okay, so r squared, and this is your 4r cosine theta, right? Because x is r cosine theta. And then you're like, aha, the r's cancel. So you get r equals 4 cosine theta. And you're like, great. So we want the one with r is 4 cosine theta. Well, that's actually both of them. So what's the difference between b and d? It's in this outer layer. Where does theta go from? Now, it's natural to always think 0 to 2 pi, but it doesn't mean it's always right. Think about our picture here. Which values of theta are we hitting our region? So it seems like we're starting, going straight down, and we're hitting our region, hitting our region, and hitting our region, and then we stop and we're going straight up. So we're not going all the way around. We just need to go halfway around. From straight down, which is negative pi over 2, to positive pi over 2. So we're looking for bounds from halfway around. And that's why D is the correct answer. So what we have is that theta goes from, not 0, negative pi over 2 to positive pi over 2. And then R goes from 0 out to 4 cosine theta. Now, what would happen if you had gone 0 to 2 pi? Well, what would happen, if you want, we can follow the story, is you first capture the top half of the circle. Now, when you swing around, because 4 cosine is negative, you're actually capturing the bottom half of the circle, and we're only up to pi. We're now going to capture the top half again, and that gets us to 3 pi halves. And then we're going to go to the bottom half again, where you are double counting. And so that's why we only want to go negative pi halves to pi halves. We do not want to double count, because that would give us the wrong answer. So anyways, there we go. It was D. Woohoo! Nice! All right, well, that was a fun set of multiple choice. But maybe we should do something else. Set up, but do not evaluate. And I have to tell you that when it comes to a Calc 3 exam, any exam, but do not evaluate, those are the prettiest words. Integrals in spherical and cylindrical coordinates that will find the volume of the shape described by z greater than or equal to 0, x squared plus y squared plus z squared less than or equal to 9, and x squared plus y squared greater than or equal to 4. Okay, all right. Well, let's think about what these pieces are telling us. Now, z greater than or equal to 0, that one is not so hard. So, because we know what z equals 0 is. That's our floor. That's the xy plane. So we are above the xy plane. So, okay, so we are above the xy plane. Now, the next one, x squared plus y squared plus z squared less than or equal to 9. Well, again, think about just what does equality look like. X squared plus y squared plus z squared equals 9 is a sphere. If we want to be less than or equal to 9, we are going to be on the inside. Okay, so this is inside a sphere of radius 3. Cool. All right, so that's that piece. And then there's this last piece. X squared plus y squared greater than or equal to 4. Well, what is that? Well, there's no z part, right? So in the xy plane, it's a circle of radius 2. And now, what are we going to do? Well, we're going to go up and down because there's no z, so it's the same all the way. So if you have a circle copied up and down, what shape are you making? It's a cylinder. Okay, so this is a cylinder. Now, are we in or out? Well, we are out because we're big. We want to be far. So this is outside. Whoops, outside. I can spell that. Outside a cylinder of radius 2. Okay, so now we have all of our pieces together. All right, now let's think about what this looks like. And our picture doesn't have to be super, super clean. Yeah, just roughly speaking, it's good enough. So we know we're above the xy plane. So we have our floor. And let's lightly sketch in some things. We have our sphere of radius 3. So we have our sphere of radius 3. Okay, so there's our sphere of radius 3. And then we have our cylinder of radius 2. And the good news is that 2 is smaller than 3. So, okay, so there's this cylinder here. And it's going to get copied up and down. And we're above the xy plane, so I won't go below the xy plane. Okay, so what's true? We want to be outside the cylinder, inside the sphere. All right, that's narrowing things down a lot. So what we have is this curious shape. It's like you took a sphere, but then you drilled a cylinder down the middle of it. And that's because what the shape is you take a sphere and then you then you drill a cylinder out of the middle of it. Okay, so there's our shape. All right. It's a sphere with a hole. All right. Well, now that's cool. And one thing that we can get right away is, I'm going to mark that here, is that we see it has beautiful symmetry around the z-axis. Oh, that's great news for us. So it's nice around the z-axis. So when you have that nice symmetry around the z-axis, how we understand things is to look in a slice. So I like to call it the ZR plane. So I'm going to slice, and since we're always greater than or equal to 0, I'm just going to be above. Here's R, here's Z. And this piece right here, you could just spin this around, and that would be your shape. So that's the slice I'm looking at. So it's like I'm just sliced down. So we have a 2. Here's 3. We have our cylinder just becomes a line. And our our sphere becomes a circle. And so there's our shape. Okay, now we're ready to start answering some questions. Okay, so we have to do this in both spherical and cylindrical coordinates. So we have to decide. It doesn't really matter which one's first. We have to do them both. And I think I'll do cylindrical first. Cylindrical tends to be very convenient. So let's make some notes here. So for cylindrical, well, because we know it goes all the way around, we know that we can say, look, 0 is less than or equal to theta, less than or equal to 2 pi. Okay, great. And that's full symmetry all the way around. And that one was kind of a freebie. Now, what about R? Well, look in the RZ plane now. Everything else comes down to the RZ plane. Well, R goes from 2 to 3. So, okay, so 2 less than or equal to R less than or equal to 3. Great, that wasn't so bad. And now, if I have a value for R, where does Z go from? Well, it goes from 0, which is the xy plane, so 0 less than or equal to Z, and up to the sphere. Now, let's think about the sphere. The sphere is x squared plus y squared plus z squared equals 9. What is x squared plus y squared going to be? See, cylindrical is like polar plus z. So this becomes r squared plus z squared equals 9 in our cylindrical coordinates. So subtract r squared, take a square root, and you get to the square root 9 minus r squared. Okay, so that's this curve here. Those are our bounds. The last thing we need to note is that, well, dv is r dz dr d theta. With all of that, we're ready to write down our answer, right? Because how do you find volume? That's the goal. Find the volume. Well, our volume is going to be the integral, triple integral, over our shape of dv. So that's going to be an integral, integral. dv is r dz dr d theta. Theta, 0 to 2 pi. R, 2 to 3. Z, 0 square root 9 minus r squared. And there we go. That's cylindrical. Cool. Now, we still have one to go. And all right, so let's turn our attention now to spherical. And this sometimes is the one that takes a little bit longer. So let's talk about things that we know for free. Theta's a freebie. If you know what happens for cylindrical, same thing happens for spherical. And we're going full circle, so we're going 0 up to 2 pi. Now, what does spherical work in? Well, we should have made notes here, but it works in theta, phi, rho. And so, when we did cylindrical, what did we work in? We worked in theta, r, and z. So what is phi? Well, phi is an angle that comes off of the positive z-axis. So it's easy to see in the RZ plane. So here is 0, and then we go until we hit something, and then we keep going until we stop. Now the stopping is the easy part. Where do we stop? We stop when we hit this angle. That's 90 degrees. So this here, this would be phi equals pi halves. And phi equals pi halves, also known as the xy plane. So, good news, we know half of phi pretty quickly. What about the other half? Well, that's where we have to be a little bit, we have to think about the question, what's this angle? Now, for that, we can take advantage of the fact that we know a couple of distances. We know this is a sphere of radius 3. So this length is 3. We also say, hey, we know this length right here. That length is 2. Oops, sorry, not 2. This length is 2. Excuse me. I was looking in the wrong place. That length is 2, so that length is 2. Okay, so what do we have? Well, we know this is 3, and that's 2. And unfortunately, that's not a really nice triangle. So what are we going to do? Well, even if it's not a nice triangle, we can think, well, what relates these measurements? The opposite side and the hypotenuse. So that's sine. Sine of phi, opposite over hypotenuse, 2 over 3. So what is phi? So phi would be the inverse of 2/3. Sine inverse. Now you could do other things as well. You could say find this missing side, which I think would be square root of 5. And then you can do tangent, you can do cosine, you can do all sorts of things. But since we already have the opposite and the hypotenuse, let's do sine. Okay, so that's phi. And yeah, you probably weren't expecting that. Now, bad news is it's a messy constant. Good news is it's a constant. We like constants. Okay, now that brings us to r. So r says, how do you relate to the center, the origin? So we go out, we start, and then we stop. Now we stop at the sphere. Okay, so I think I said r, I should have said rho. So rho stops at the sphere of radius 3. So rho is at most 3. Where do we start? Well, we start here. Well, where is that? That's your cylinder. That was your x squared plus y squared equals 4. Or we said, hey, that becomes r equals 2. And we said, hey, hold on a second there. We know something about spherical coordinates, right? So what do we know? We know for spherical, we'll write some things down. X squared plus y squared plus z squared equals rho squared. We know that rho cosine phi is equal to z, and we know that rho sine phi is equal to r. So if we have r equals 2, well, that tells us what? It tells us that rho sine phi equals 2. So solve for rho, you get, rho equals 2 cosecant phi. So that's the bottom bound, 2 cosecant phi. All right, good. And now we say, oh, sine inverse and cosecant, maybe that's not so surprising that they're so close to each other. The last thing, dv. So for spherical, do you remember the song? Rho sine of phi, d rho d phi d theta. Merrily, 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 merrily. Exams are just a dream. All right, so we're integrating dv, that finds volume. Integral, integral, integral. We need a little bit more space because we have a little bit more complicated things to write. dv is our rho sine of phi. D rho d phi d theta. Theta, 0 to 2 pi. Phi goes sine inverse of 2/3 to pi over 2. Rho goes from 2 cosecant phi up to 3. And there we go. There's the volume in terms of spherical coordinates. And woohoo! We set them up and we didn't have to evaluate it. So nice! Woohoo! Let C be the closed curve that starts at 2, 0. So we start here. Then moves along the quarter circle, x minus 2 squared plus y minus 2 squared equals 4. So that's this piece up to 0, 2. And then back along the quarter circle, x squared plus y squared equals 4, back to 2, 0. So you see there's an arrow here. It's a little bit small. I'm going to make it a little bit bigger. And I'm going to make an arrow down here just to help us really, really make sure we understand what's going on. Compute the following line integral. Integral around C 4y cosine squared x plus arctangent of x squared dx plus sine of 2x plus e to the y cubed dy. All right, now there's some hints about what this problem is about. Big hint number 1, and it's seen in the integral. It's also seen in the picture. You see that little halo, that circle? that tells us this is a closed curve. All right, when we see integrals on closed curves, we start thinking Green's theorem. Okay, so we should remind ourselves what Green's theorem says. And I should tell you, calculus teachers love Green's theorem. And we'll see why. There's a second clue, but let's first off write it down. So Green's theorem says that the integral along a closed curve of m dx plus n dy is equal to the integral over the region R of n sub x minus m sub y dA. All right, so that's Green's theorem. Now, there's a little bit I'm leaving out. We'll get to that in a second. So let's first off understand what are C and R. C, we were told. What is R? Well, because it's closed, it bounds a region. Okay, so where is that? In our case, it's just this sort of strange shape. Okay, so here we go. There's our region R. Okay, so here's our region R. Now, some other comments. I said there was another clue. At least I hinted there was another clue. When you look at this line integral, there's pieces that you do not want to do. They are, we do not want to try to integrate arctangent x squared. We do not want to try to integrate e to the y cubed. So when you see things which are terrible, that is a huge clue. Do not do it literally as it's written. Use the tools to make it something which is nice. It's almost like we want you to find an answer. Okay, so why does this being messy clue you in on Green's theorem? Well, notice that we're going to take the part that's attached to the dy and take the derivative with respect to x. There's no x there. That's gone. The part that's attached to the dx, we're going to take the derivative with that with respect to y. There's no y there. That's gone. So when you see really messy stuff, that's a clue that there should be a theorem that lets you somehow get rid of that messy stuff. And in this case, it's Green's theorem. Now, there's one thing we haven't mentioned, and I know a lot of you have already said, oh, Steve, there's a problem here. And let's go ahead, the elephant in the room. Orientation. Okay, so orientation matters. So you have to keep track. Now, how do you know how to orient? Well, don't think counterclockwise or clockwise, because that can get you in trouble when you start having regions with holes in the middle. So we want to be able to handle all of them. So just remember the song. To the left, when you walk the curve, keep the region to your left. All right, so let's walk our curve. Is our region to the left? It is not. Our region is to the right. So our curve is going the wrong way. How do we fix that? Well, it turns out orientation comes down to plus or minus. So you know that plus or minus you've been learning about ever since you were a young person? It's all about orientation. It always has been. We just haven't said it very well. So we say, oh, well, if our orientation on our curve is going the wrong way, well, then we just throw a minus in and that fixes it. Okay, so keep that in mind and let's do the problem. So this becomes equal to minus integral over our region, and I'm just going to make some notes here. This is our m, and this is our n. And before we get any further, just so people understand, orientation is backwards. So that fixes it. Okay, so that's why there's the minus. And okay, so we have our n sub x. So take the derivative of sine of 2x with respect to x, that's 2 cosine 2x. And the derivative of e to the y cubed goes away. Okay, so there's our n sub x, nx. And then subtract, take the derivative with respect to y. Our tangent x squared goes away. We have 4 cosine squared x. Okay, there's our m sub y. And now we just have to integrate that with respect to our region. Okay, good. Now, that's better. It'd be nicer if we didn't have to have any variables involved. 4 cosine squared x and 2 cosine 2x. Well, that's interesting. There's something in the back of our mind. It's going, wait a second, cosine squared x, cosine 2x, there's something connecting them. Do we remember though? Let's think about it. Okay, so what do we know? We have trig identities. We might as well write down a couple of useful ones. We know, for example, sine squared plus cosine squared equals 1. Classic. I don't think that's going to help us much. We know sine of 2x is 2 sine x cosine x. Okay, yeah, that's, again, classic. Everyone loves a good cosine, sine 2x identity. There's a cosine 2x, which says that's cosine squared x minus sine squared of x. Like, oh, that's getting closer to home. And the other two, I'm skipping the secant and tangent one because there's no way that can be related. Cosine squared x is 1/2 cosine of 2x plus 1/2 and sine squared of x is minus 1/2 cosine 2x plus 1/2. Okay, so those are our collection of trig identities. And we say, hey, you know what? Look at this power reduction one. Let's see what this says. So let's go ahead. We're going to multiply in the minus sign. And let's do that. So I'm going to multiply the minus in. I'm going to go ahead and write this as integral of our region 4, because minus minus makes plus 4. Cosine squared x is 1/2 cosine 2x plus 1/2. And then we're going to subtract 2 cosine 2x. All right? So I'm using our power reduction. Now, that's 2 cosine 2x minus 2 cosine 2x. What happens? They cancel. Like it was planned to be. Because it was planned. In fact, it was very carefully planned. And don't forget the dA, because I did that. And so we're left with 2. Aha! So what is that? Well, if you're integrating a constant, that's really 2 times the area. Like, oh, neato. So all we have to do is figure out how much area there is, double it, and we've got our answer. Now, we're going to take advantage of a couple of things. One is there's symmetry here. So if you were to splice this down the middle, that the area on the below side and the area on the top side match. Now think about this part, the top part. Well, what you can do is you can take a quarter circle of radius 2 and subtract the triangle, and what you're left with is just that little half of the eye. So what's the quarter of a circle? Well, that's 1/4 pi 2 squared. Here, you can have 1/2 base height. So you'll end up with pi minus 2. Okay, so this area is pi minus 2. So if we double that, we get that the area of R, this part, is 2 times pi minus 2. But remember, we have to double that. And so our final answer is going to be 4 times pi minus 2. And that's our answer. Ah, whoo, good, good. And yeah, see, notice it looked like it was going to be really hard. Then it looked like it was going to be mildly hard. And then it was like, wait, there's no integration at all. It's all geometry. We love geometry. It's great. Woohoo! Yes. All right. So, but know your Green's theorem. Pay attention to your orientation. Know your identities. Work the problem. Work the problem. Find the integral from 0 to 1, integral y squared to 2 minus y squared of 24xy minus 24y cubed. Divide that by 1 plus x plus y squared cubed dx dy. Wow. We're going to have to find that? And it says, using the substitution, oh, that might be helpful, x plus y squared and x minus y squared. Simplify your answer as much as possible. Now, it looks like they've given us the picture. Good for them. I appreciate that. And we can sort of understand now what's going on. So we see we're going from 0, and then this will be up here at 1. And then we have our curves. Now here, this is x equals y squared. So that's this curve here, x equals y squared. And then we have x equals 2 minus y squared, which is this curve on the other side. So x equals 2 minus y squared. All right, now we have a substitution problem. These also are tied to Jacobian. Sometimes you might hear them referred to as Jacobian problems, change of variable problems, change of coordinate system problems. There's lots of different names to them, but at the end of the day, they all sort of have the same spirit. There's 3 parts to our integral. We need to update all 3. The function, the region description, and how we break things up. So breaking up, that's the important part, right? And you might think it's like this old song, breaking up is hard to do. No. We have tools. So the first thing I always recommend is start with Jacobian. All right, so our sort of long-term plan, just so we understand, our long-term plan is we're going to rewrite this in terms of u and v, and then, fingers crossed, it's integrable in u and v. So we start with Jacobian. All right, so we'll call it step 1, Jacobian. Now for this, there's a nice convenient formula. We have u and v in terms of x and y. So we're going to take our partial derivatives. We're going to take u sub x, u sub y, v sub x, v sub y. So we're taking all our partial derivatives. If you get it wrong, don't stress too much about it. It's really hard to get the Jacobian so wrong that it's going to cause you a problem. It's very forgiving. It's like your dream calculus instructor. Super, super forgiving. All right, so here we go. U sub x, 1. U sub y, 2y. V sub x, 1. V sub y, minus 2y. Now, if you take this, you'd get what? You'd get minus 2y, minus 2y. Now, that's minus 4y. But here's the thing, is when we take the Jacobian is measuring expansion, contraction, and so we always take absolute value. Okay, so what the moral here, the punchline is that we get that 4y, that's the absolute value of this, dx dy equals du dv, or dv du. Order doesn't matter right now. The key is, how do these relate? Okay, now, good. With the Jacobian out of the way, we're ready to move into the function. We need to account for that 4y. And so we say, all right, well, let's look at our current function. We're going to split it into 2 parts. The bulk of the function, okay, the bulk of it is going to be, well, maybe let's start with the small part. Part of it is going to go into this 4y. The bulk of it's going to be what's left over. So let's see, can we pull the 4y out? And it looks like we can. So we have a 24. I'm going to pull that out as 6 times 4. So I'm going to think of this as 6 times x minus y squared times 4y. Then downstairs, I'm going to think of this as 1 plus x plus y squared cubed. The reason I'm going to think of it that way is because that's what it actually is. It's a good reason to think of it that way. But okay, so the punchline here is we're pulling a 4y out because of the Jacobian. So we're in step 2 phase, which is our function. Now, here, this is going to get absorbed by the du dv. So that we don't need to do anything with. This part we do need to do something with. We say, all right, we need to use our new variables to replace these pieces. So we start thinking like, well, what can we do with this x minus y squared? And the good news is we don't have to think very hard. It's like, hey, that looks a lot like the v. And like, it does look like the v. And we say, okay, cool. So that looks like 6v upstairs. All right, what about the x plus y squared part? That looks like a lot like the u. What? It's almost like it was meant to be because they planned it that way. And they did. They did plan it that way. Oh, those devious planners planning things so that they work out. All right, so we've gotten our Jacobian. We've gotten our function. So this is step 2, function. You always want to do Jacobian first before function. Sometimes your Jacobian is 1, and it doesn't matter, but sometimes it's not, and it does. And pay attention onto where it goes. When in doubt, just think about, what is this a function of? Is it a function of x or y, or a function of u and v? If it's a function of x or y, it's then that times dx dy equals du dv. If it's a function of u and v, then it's that times du dv equals dx dy. So it's not actually too bad. Once you get the hang of it, it's like, oh yeah, it kind of has sort of a built-in mechanism to take care of itself. Okay, so we've gone Jacobian, we've gone function. That leaves us with bounds. Okay, so let's talk about bounds. We must not forget the bounds, the bounds, the bounds. Now, what I recommend is don't necessarily grab the bounds here. Think of the picture. What curves actually bound the region? Because you might say, hey, what about y equals 1? It's not bounding the region. It's literally just that single point. And that can mislead you when you're putting your new region together. So don't focus on that. Focus on, hey, what curves are actually bounding my region? And there's 3 of them. It's kind of like a triangle. So we've already marked 2 of the functions. Let's mark the 3rd. It's the x-axis, also known as y equals 0. Cool. So here we go. For the 3 curves, let's start with x equals y squared. Now our mindset is take the existing curves, make them look like things involved in u and v. And we see an x and a y squared. We say, hey, you know, if you move that y squared across, this becomes x minus y squared equals 0. And hey, that's a v. So that becomes v equals 0. Cool. This curve, x equals 2 minus y squared. Well, again, move the y squared across. X plus y squared equals 2. And x plus y squared, that's a u. So u equals 2. Now, the 3rd one, y equals 0, you're probably thinking, oh, okay, Steve. Ha ha ha. You're not going to get this one. You're right. It's not going to be easy to automatically convert it. So when in doubt, think about, well, let me just take what it is and see what it becomes. So suppose you put y equals 0 into both these equations. So if you put y equals 0 in, that leads to a pair of equations, namely u equals the x and v equals x. But wait, if u equals x and if v equals x, how is that possible? It's only possible if they equal each other. So it becomes u equals v. So let's sketch our region. I like to put U on the horizontal axis and V on the vertical for no other reason than U comes earlier in the alphabet. That's literally the only reason I do that. There's nothing sacred about that. Okay, so we have a couple of curves. I'll change colors here just to highlight where they are. We have U equals 2. So let's say that's U equals 2. V equals 0. Okay, we'll say that's V equals 0. And then we have U equals V. U equals V. And now we say, oh, there is a shape here. So this triangle, which is a proper looking triangle now, that's our new region. Okay, so that's our UV region. All right, well, now that we've taken care of the three pieces, we've got our Jacobian, we've got our function, we've got our bounds. We're ready to put it all together and say, so what is our new integral? Okay, so it is integral 6v over 1 plus u cubed. The 4y goes into the du dv. Now the question, do we want to do du dv or dv du? And why? Well, remember, we actually have to integrate this. Which one of these two would you rather integrate? Would you rather integrate with respect to v or with respect to u? And at this point, I would not want to integrate this with respect to u. But v, that's looking pretty good. So let's go dv du. So we get a choice. So choose wisely. Choose the thing that's easy to integrate with respect to. Now let's think about the bounds. Where does u go from? Well, we're along the bottom edge. U goes 0 to 2. Given a u value, where does v go from? Well, we go from v equals 0, the line, up to v equals u. So it's from 0 up to u. All right. Now, this already looks way better. And let's go ahead and start working this out. So this becomes integral 0 to 2. When we integrate with respect to v, the 1 plus u cubed stays as is. The integral of 6v becomes 3v squared over 1 plus u cubed. And we're evaluating from v equals 0 to v equals u. Well, when you plug in 0, you get 0. Nice. Plug in u, you get u, right? So this becomes the integral 0 to 2 of 3u squared over 1 plus u cubed du. Now, previously 1 plus u cubed by itself, we didn't want to touch. But now there's that 3u squared upstairs. That is going to give us an extra boost because we can make a nice substitution. If we let, we've already used u, v, work, and x and y, right? We've got to work our way through the alphabet. Good news is there's a lot of letters, and we can always make up new ones. W equals 1 plus u cubed. Then dw would become 3u squared du. And that's exactly what we have up there. So it's dw over w. Our bounds, well, plug in 0, you get 1. Plug in 2, and you get 9. So this becomes log of w. Evaluate that from 1 to 9, which is log of 9 minus log of 1. Well, log of 1 is 0, and so we end up with log of 9. And it says simplify. I think that's as simple as we can possibly hope for. Log of 9. Ah, whew, that was a good one. A nice workout problem. But, you know, it sounds like we did a lot, but if you break it down, you say, okay, know your steps. Do your Jacobian computation. If needed, pull that part out. Figure out what the rest of the function looks like. And then go for each one of your bounding curves. Translate that into u and v so you get your new region. Set it up, and then life will be good. Nice. Practice, and this will become second nature. Well, close enough, right? Enough that you'll be fine. Practice, right? You can do this. You can do this. Let G be the surface which is the portion of the cone z equals 4 minus root x squared plus y squared lying above the xy plane, also known as z equals 0. Given the surface has a density delta xyz equals square root of x squared plus y squared, find the center of mass of G. Okay, cool. All right, so let's make sure we understand this problem because there's a lot of fun stuff going on here. First off, we have an idea of what it looks like. It's a cone. Now, the reason we think it's a cone is because it says it's a cone. So that's a pretty strong clue. It's hard to go against that one. But, okay, so what is that cone? Now, z equals square root of x squared plus y squared. That's a cone that usually goes straight up. Minus turns it so it's going straight down. The 4 moves it up. All right, so what do we have? Well, we're up here at 4, and we have this cone that's going to go down. Okay, All right, so there's our cone. Now, let's be perfectly clear. I'm going to stop here and focus on something. It's not a solid cone. We are only doing a surface, so it's just the surface of the cone. So if you've ever seen, for example, an animal after it's gone and had a mild surgery, they put that cone of shame around. That's what we have. It's a cone, but not of shame, of joy and pleasure, because we get to do calculus. So it's just a surface, and we have that. It's so think about metal plate or that's been shaped into a cone, whatever you like to think of. It's not uniformly dense. So how does the density vary? Well, what happens is you have square root of x squared plus y squared. And so that's related to your radius. How far you are from your z-axis. So the further out you are from your z-axis, the denser you are. So the dense parts are actually nearer the bottom, whereas the thin parts are near the top. So, okay. We also have that there's a lot more stuff at the bottom. So, eyeballing this in, that tells us some information that, in the up-down direction, it should be fairly low for the center of mass. There's one other thing we can make an observation of, is that we have some beautiful symmetry here. And that is that we can spin around the z-axis. So symmetry around the z-axis tells us what? Well, it tells us that, and when I talk about symmetry, there's two things. Symmetry of shape, symmetry of density. So symmetry around the z-axis, that tells us that our center of mass is on the z-axis. Well, what does that tell us? Well, that tells us that our center of mass has to look like 0, 0, z bar. Okay, so we've already found 2 out of the 3 coordinates. We're 2/3 done. Now you might think, okay, does that mean we got 2/3 of the point? No, we probably got 1, but it's better than 0. All right, so we know 2 out of our 3. So how do we find z bar? Well, let's take a moment to think about that. Okay, all right. That was cheesy even for me. So here we go. Z bar is found by a ratio. It's the moment with respect to the xy plane divided by the mass. And you might say, okay, but how do you find those? Well, mass you find by integrating over your surface your density, the surface area. Okay, now that's your mass. Your moment, and this is true for all moments, is you integral over your, again, same object, density, and distance. There's more to write in here. Can we fit it all in? Yeah, I think we can get it all in. DSA. All right, so we have these basic building blocks, right? Okay, so we have these facts. And so what we need to do is go ahead and run these computations. Now, how are we actually going to do this? Well, if you think back to when we did a line integral, and we did one earlier on this practice exam, we said, oh, we're going to convert it into an integral from t, right? From like, a to b. So instead of like going on some sort of curvy line, we're just going to like, hey, find a way to reparameterize it, rewrite it in terms of t. Same philosophy with surfaces. So we have this surface, so what we're going to do is, if it's a two-dimensional object, we're going to push it down into the xy plane, and we're going to work on that. So that's our mindset, is, okay, push it down. Now, how do we get there? Well, imagine that you were looking down the z-axis. You're looking from way up above. When you look from above, so we're looking straight down, what do we see? What do we see? We see a circle. And in particular, what we're really seeing is this circle, right? The outer edge where it hits the xy plane. And so what we're going to do is we're going to push it, and we're going to call that region R. Now, what do we know about this region R? Well, we can actually work it out. That's z equals 0. So this is x squared plus y squared equals 16. Right, so z equals 0. Move it across, square both sides. It's a circle radius 4. So, all right. So that's R. So we're going to push our integrals into R. Now, that's good news. So that's how we're going to actually do the surface integrals. But to pull that off, we need to get a handle on DSA. So let's work on that piece now. Okay, so here we go. What is DSA? So that is the square root of 1 plus fx squared plus fy squared. And times your dA. Now, I'm going to almost surely forget to keep writing the dA, but imagine I was very good at remembering how to write stuff. So let's take it. This right here, this is your f of xy. All right, so this becomes the square root of 1 plus, so when we take a derivative, the 4 goes away. We're going to get minus 1/2 x squared plus y squared to the minus 1/2 times 2x. And that's going to be squared plus minus 1/2 x squared plus y squared to the minus 1/2 times 2y, and that will be squared. All right, now, if you square all these things, and notice that the 2's cancel, so that's some good news for us. The minuses go away. So what do you have? You have 1 plus, in the first term, you have x squared over x squared plus y squared. In the second term, you have y squared over x squared plus y squared. All of this is inside your square root. And as I predicted, I forgot the dA, so I'll write the dA again. Now, our great aha is upon us. X squared over x squared plus y squared over x squared plus y squared equals 1. Because you can add the numerators. So you really have 1 plus 1, which makes this a grand total of square root of 2. Okay. Whew. All right. So now we have our tools. We are ready to write our pieces. So let's begin. We'll start with our mass. So mass is the integral over our surface. Our density function is what's given to us, square root x squared plus y squared, and then DSA. Now, it's going to become integral over our region, because we're pushing the integral down into our region. of what? Well, square root of x squared plus y squared becomes square root of x squared plus y squared. And then dsa becomes square root of 2 dA. Now, how do we integrate? Polar, right? It's a circle. Of course it's going to be polar. What else could it possibly be? All right, people love polar. What can I say? Okay, so here we're going to just make some comments. Integral, the square root of x squared plus y squared becomes r, square root of 2, then there's an r, dr, d theta. Theta goes 0 to 2 pi, all the way around, circular symmetry. R goes from the center out to the edge of your circle. It's a circle of radius 4, so 0 up to 4. Okay, so now this becomes square root of 2. This pulls out. Then you can split it up into the integral from 0 to 2 pi of d theta and integral 0 to 4 of r squared. Well, okay, that's square root of 2. Integral of 0 to 2 pi, d theta is 2 pi. And here we get 1/3 r cubed. Evaluate that from 0 to 4, which gives us, well, plug in 0, you get 0. Plug in 4. 4 cubed is 64. Good. And there's a 2. So this gets us 128 divided by 3 times square root of 2 times pi. Okay. Good. Pause for a second here. Is this our z bar? Nope. It's our denominator. Okay. So what do we need to do? Well, we need to celebrate our successes. Woohoo! And continue on with the computation. So now we need to switch gears and we're going to say, all right, well, let's now focus on, and I'm going to choose a different color here. Let's focus on mxy. Take a moment, right? Yes, of course. Take a moment. All right, so here we go. So what's the difference? Well, it's very similar. So mxy equals the integral on our surface, our density, square root of x squared plus y squared, and now our distance. So what's the distance if I'm at some point on my cone? So here's my cone. What's the distance down to the region? To the xy plane. And the answer is it's z. All right, and then we have dsa. Well, we're going to rewrite this in terms of this integral in terms of r. Okay, so this is equal to the integral over r, square root of x squared plus y squared. Now, everything's going to be in terms of x and y. I can't have z, so I have to replace it. But how do I do it? By the relationship. The surface has z in terms of x and y. So, for minus square root of x squared plus y squared. And then the dsa, square root of 2 dA. All right. Good. Good. Now, same thing as before. We're going to switch to polar. All right, so this equals integral 0 2 pi, integral 0 to 4, and then we have our r times 4 minus r times our square root of 2 times our r dr d theta. Okay, so let's make sure we understand. There's our first r, 4 minus r, square root of 2, there's our dA. Okay, well, this, again, we can pull out. There's a square root of 2, integral 0 to 2 pi, d theta. And then there's an integral 0 to 4, r times 4 times r, that's 4r squared. And then r, that's r cubed. So 4r squared minus r cubed, dr. Okay, well, the first part, that's quick enough, we can do that. That's 2 pi. Here, this will become 4/3 r cubed minus 1/4 r to the 4th. And then we're going to evaluate from 0 up to 4. And, okay, 4/3 times 4 cubed. Well, 4 cubed is 64. Times that by 4/3, well, it's a number, right? Well, let's just say that's 4/3 times 64. Now, what do we have here? Well, we have 1/4, 4 to the 4th. Now, 4 to the 4th and a 4th I can cancel off, and that's really 4 cubed, which is really 64. So this is really 1/3 times 64. All right, now we are going to multiply these pieces together. So we have square root of 2 times 2 pi times 1/3 over 64. So, all right, 2 times 64 makes 128 pi square root of 2 over 3. So 128 divided by 3 times square root of 2 times pi. All right, now that's our moment. Okay, so we've done our moment computation. Now, is this z-bar? No. Something eventually has to be z-bar, Steve. Well, we're ready to do the computation, right? We're going to take our moment divided by our mass. So we have that z-bar is equal to, make sure you pick the right one, the moment goes on top, 128 thirds square root of 2 pi, divided by, the mass goes on the bottom, 128 thirds square root of 2 pi, and if you do that computation, it simplifies a little bit down to 1. And at this point, you're like, are you serious? All this work for 1? Or you could be like, wow, that's amazing. That's beautiful. I love math. Let's do this some more. All right. Well, anyways, that was the z-coordinate. Let's put it all together so that our final answer is 0, 0, 1. And if we think back, we said, hey, there's more stuff at the bottom. It's heavier at the bottom. It should be biased towards the bottom. And if you think about it, that's what this shows. So even though the cone is 4 high, the center of mass is only at height 1. So it's definitely, there's bias towards the bottom. So that's actually a pretty good and reasonable answer. Ah, what a fun set of practice problems. Before we leave, I want to make some comments. You're probably looking at this and saying, like, how am I supposed to do this in 75 minutes? You're probably not. This is meant to be a more challenging set of problems that will help you prepare for what you will see on the exam. We are doing the harder stuff here, so that what you see on the exam will be like, I can do this. We also spend a lot more time talking about things. The good news is that when you're taking the test, you don't have to explain it to everyone. You just have to explain it to yourself, and usually that's a lot faster. So you will be okay with time as long as you've been preparing. So don't stress about the length of this video. You'll be okay. These are more challenging, but they are helpful to do. And so the other thing is, of course, if you've gone this far, you're already amazing. We already believe in you. And so keep doing the work. You'll be okay. You can do great things. Get as much practice as you can. Be ready, and don't be surprised, because there's not that many things we can ask you. So prepare. All right. I hope you have a good experience. I hope you do well on your exam. And let's all have a great time. Take care.